Okay, so this is the final video for chapter 6. We're going to cover the final way of sort of judging an estimator, which is called mean squared error. And this is actually a good way of comparing two estimators. Okay. All right, so pause, copy, press play. This example continues on the next panel. All right, so we've got theta hat, an estimator of a population parameter theta. The mean squared error of theta hat is defined to be the expected value of the quantity theta hat minus theta squared. So that's the definition, similar to the definition of the variance. And similarly, it can be shown that that expected value is equivalent to the variance of theta hat plus the square of the bias of theta hat. And this will be the form of mean squared error that we actually use on a day-to-day basis to compute things, okay? Now, as this alternate definition of the mean squared error shows, mean squared error is trying to balance looking at the bias and looking at the variance of the estimator. So it's combining these two measures. And remember, we'd like a low bias, 0 ideally, and we'd like a low variance. Remember, a high variance means that if you actually compute an estimator from a random sample, you could be considerably away from the expected value of the estimator. Okay. All right, so it combines bias and variance measures. And because it does with addition, we want both of these two pieces to be small. So the lower the mean squared error, the better the estimator. And note that if your estimator of theta hat happens to be unbiased, then that's all a 0. And the mean squared error of theta hat is simply the variance of theta hat, okay? All right, so we're gonna compare two estimators, and we're gonna see that via mean squared error, we're gonna see that could be sometimes a complicated answer. So we're gonna start with a binomial distribution. So X is gonna be a binomially distributed random variable. And if you remember, that means X is actually the number of successes in n Bernoulli trials, each with probability of P. And I've got an expected value of X to be n times P, and the variance of X to be n times P times 1 minus P. And we're going to use these, okay? All right, so I'd like estimators of P. So the first one's going to be the sample proportion. It's going to be the number of successes divided by the number of trials. I'm going to call that one P1 hat. The second one is going to be P2 hat, and that's going to be the number of successes plus 1 divided by n plus 2. Why? Why not? Okay. And the question is, which of these two estimators of P has the lower mean squared error? All right, so let's crank that out. And hopefully things aren't too small that you can't see them. All right, so pause, grind out that computation, and then press play. All right, so up here, I'm calculating the mean squared error of P1 hat. Down here, I'm calculating the mean squared error of P2 hat. And down here, I'm comparing those two mean squared errors, okay? All right, so up here, P1 hat was X over N. So its expected value, I can drag the 1 over N out. The expected value of X is N times P. Since X was binomially distributed, that cranks out to a P. So great, P1 hat's an unbiased estimator of P. Variance of P1 hat, well, I can drag the 1 over N out as 1 over N squared, and I know the variance of X is N P1 minus P, so a little simplification, I get P over P times 1 minus P over N. Bias, if you really want me to calculate the bias, it's the expected value of the estimator minus P, that's P minus P, that's 0, because it was unbiased. So then now calculate the mean squared error, it's the variance plus the square of the bias, so there's the variance, there's the square of the bias, and there's the MSE value for P1 hat. Cool. P2 hat. All right, expected value, well, P2 hat is X plus 1 over N plus 2. Drag out the N plus 2. Expected value distributes over addition. The expected value of 1 is 1. The expected value of X is NP. So the expected value is NP plus 1 over N plus 2. All right, well, let's go calculate the bias. So there's the expected value of P2 hat minus P. And with some common denominator work, I get 1 minus 2P over N plus 2. Okay, variance. There's P2 hat, drag out 1 over N plus 2 squared. Variance of X plus 1 is the same as the variance of X. Shifting the data up 1 doesn't change the variance of it. And the variance of X is NP1 minus P. So there's the variance of P2 hat. And then the mean squared error, there's my variance plus the square of my bias, and some simplification cranks out to equaling that bad boy, okay? So I need to compare these two mean squared errors. And you'll note they're both a function of n, the number of trials, and p, the probability of success. So the answer of which of these is smaller might depend on your n and your p. For example, for n equals 16, so replacing all the n's in both of these with 16, I can graph both of these as functions of p. P, the probability goes from 0 to 1. And so on the vertical axis, I'm graphing the values of these mean squared errors. Black is the value of the MSE of P1 hat, and red is the MSE of P2 hat. And remember, we want the lower MSE. So for n equals 16, if the probability is close to 0 or close to 1, it looks like P1 hat has the lower MSE. But if the probability P is somewhere in the middle, so around either side of 0.5 for a fair ways, it looks like P2 hat has the lower MSE than P1 hat. So sometimes it can be a challenge to use MSE, right? But it's a measure of how good an estimator is. It's a measure of having both low bias and low variance, ideally. Okay, and we'll use it quite a bit in the chapters to come.